All right, welcome to the Explainer. Have you ever wondered how an AI goes from being just a know-it-all to a genuinely helpful companion? Well, today, we're diving into that final, super crucial step in their training, the part where we teach them not just to be smart, but to actually get on our wavelength. Let's jump in.
So, we've got these amazing language models, right? They can write code, they can summarize dense articles, they can predict the next word in a sentence like magic. They are masters of language. But how do you get them to go from being a technically perfect word predictor to an assistant you'd actually want to talk to? The answer is all in this final stage of training, a stage that teaches them something very human: judgment.
And this is the exact problem we're talking about. See, without that final training step, this is the kind of response you get. I mean, technically the AI isn't wrong, but it has completely 100% missed the point, right? It's missed the emotional context. It's smart, sure, but it's not aligned with what a person would actually find helpful. This is exactly what we need to train out of the model.
Okay, so to get how we fix this, we've got to look at our AI student after it's already done its homework, so to speak. It's gone through two big phases. First, pre-training, where it basically ingested the entire internet to learn grammar, facts, how to reason. Then, fine-tuning, where we showed it high-quality examples so it could learn to follow instructions. So by this point, it's already a genius, but it's a very, very raw kind of genius.
So what you end up with is what we call a supervised fine-tuned model, or SFT for short. And you can think of it like this. It's a genius who's memorized every single textbook and can follow your directions to the letter. But the problem is, it has zero social skills. Absolutely none. It just doesn't get the nuance, the unwritten rules of how people actually talk.
Right, so to fix that whole teddy bear problem, we can't just throw more facts and instructions at the AI. It's already got plenty of those. What we need is a totally different, a third step in its training. We have to teach it something way more abstract: our preferences. And as you can imagine, teaching something like preference is a whole different ballgame than just teaching information.
And this analogy right here, this gets to the absolute core of the solution. Just think about it for a second. Trying to write a perfect, helpful, amazing response to every single question from scratch, that's insanely hard, even for us. But if I show you two different responses and ask you to pick the better one, well, that's way, way easier. You just point and say, yep, that one. And that right there is the big idea behind preference tuning.
So why is this third step so critical? Well, for a few big reasons. First, trying to create a perfect data set of the right answer for every single situation is, it's basically impossible and super expensive. It's way more efficient to just collect these preference pairs where a human says A is better than B. This also gives us a powerful way to send negative signals, to teach the AI what not to say, like don't be blunt and unhelpful like that. And that's something regular fine-tuning just isn't very good at.
Okay, so how does this actually work in practice? Well, the first big method that really changed the game in AI alignment is called RLHF. The best way to think about it is like we're putting our AI student into this intense training program. It's got a dedicated coach and a super strict judge scoring its every single move. That stands for reinforcement learning from human feedback. And, the name kind of gives it away. It uses feedback from actual humans to build an automated judge, which we call a reward model. Then, this judge basically supervises the AI's training, giving it a thumbs up for good responses and a thumbs down for bad ones, always pushing it to improve. Let's really get into the nuts and bolts of how this works.
So it happens in two main stages. Stage 1, we train the judge. We take all that data from humans, tons and tons of examples of this is better than that, and we use it to build a specialized AI. This is the reward model, and its only job in life is to score the AI's answers. Then comes stage 2. We use that automated judge to train our main AI. The AI basically practices over and over, generating responses and trying to get the highest score it can from the judge. It learns what we prefer through pure trial and error.
Now, the math that makes this judge work is actually pretty clever. It's trained using something called the Bradley-Terry formulation. And all you really need to know is that this is a statistical method that's really good at finding the hidden patterns in our choices. It lets the model look at thousands of human preferences and then build its own system for predicting which of two new responses a person would probably like more. It becomes this powerful automated stand-in for our own judgment.
But, and this is a big but, here's where things get tricky. You can't just tell the AI, hey, go get the highest score you can. Why not? Well, because it might cheat. It might find some weird loophole to get a high score from the judge without actually being helpful. That's called reward hacking. Or even worse, in its race to get a good grade, it could just forget everything useful it learned before. We call that catastrophic forgetting.
So, how do you stop that from happening? Well, we put it on a mathematical leash. It's called a KL divergence penalty, which sounds fancy, but it's really just a way to measure how far the new model is straying from the original one we started with. If it drifts too far away, starts forgetting facts, or gets obsessed with just the score, it gets a penalty. This leash is what keeps the model grounded, making sure it holds on to all its original knowledge while it learns these new social skills. Now, even though RLHF is super powerful, it's a total beast to manage. The whole process is incredibly complex. You're juggling 4 different models at the same time. It can be really unstable, difficult to tune, and get this. If you find a problem with your reward model judge, you often have to scrap the whole thing and start the entire expensive process over. It's just a really high-maintenance, high-cost way of doing things.
And all of that complexity, all of that cost, naturally led researchers to ask a really important question. Is there a better way to do this? I mean, do we really need all this complexity? Do we need a separate judge and the whole reinforcement learning setup and 4 different models running at once? Couldn't there be a simpler, more direct way to teach the AI what we want? Well, it turns out the answer is a big, resounding yes.
And that brings us to Direct Preference Optimization, or DPO for short. This is a much newer and honestly a more elegant approach. It gets you pretty much the same result as RLHF, but in a way that's so much more streamlined. The big move? It completely skips building a separate reward model and instead just teaches the AI our preferences directly.
And when you put them side by side, the difference is just striking. RLHF is a complex reinforcement learning headache. DPO cleverly reframes the whole thing as a much simpler supervised learning problem. Look at this, it cuts the number of models you need from 4 all the way down to 2. And that means the whole process becomes more stable, a lot cheaper, and just way, way easier to handle.
The real genius of DPO comes from this brilliant mathematical insight. What the researchers figured out is that you don't need to build a separate judge, because in a way, the judge is already hidden inside the language model itself, in its probabilities. The title of the paper that introduced DPO says it all, really. Your language model is secretly a reward model. DPO just figured out how to find the key and unlock it.
Okay, so after all this complicated math and these intense training methods, whether we're talking RLHF or DPO, what does it all mean for us, the people actually using these things? What's the real, tangible difference? What does an aligned model actually feel like?
Let's circle back to our teddy bear example. The before model, the SFT model, it gives you a factually correct answer, but it's pretty blunt, right? Now look at the after model. It gives you the exact same information, but the tone is completely different. It's gentler, it's more empathetic, it gets the emotional subtext. It's not just factually correct anymore, it's actually helpful.
And that's really the whole journey in a nutshell. Preference tuning is what takes that raw, unfiltered genius and gives it some polish and social grace. It's the final step that transforms a powerful but kind of awkward tool into a sophisticated, genuinely helpful, and, well, a more human-aligned companion.
Which brings us to a final, really big thought. This entire process is about baking human preferences right into the AI. But that opens up a huge question. Whose preferences? As we get better and better at making these models reflect our values, the challenge starts to shift. It becomes less about the tech and more about the deeply human and complicated process of deciding which values we want them to have in the first place. And that's a conversation that involves every single one of us.